science progresses independent of the whims of jealousy and human nature. So physics will march forward no matter how jealous people are or how much backstabbing there is, because that's human behavior. You can't stop it. That's just the way it is.
Welcome, everybody, to the Into the Impossible podcast. I am your fearful host, Dr. Brian Keating, and this is now Professor Michio Kaku's second appearance on the Into the Impossible podcast because of a mistake by an unnamed podcast software, which I will not repeat. But anyway, today's going to be even bigger and better than ever because so much has happened just in the week or so since I first interviewed Michio, and he is so gracious and so kind to come back, given his busy schedule and his newly christened best-selling book, The God Equation, which is one of my favorite books in recent memory. Michio, how are you?
Very good. Honored to be on your show.
It's really such a pleasure, and I want to congratulate you from all of us in the Arthur C. Clarke Center for Human Imagination on not only the success of the book, in terms of commercial success, but in terms of the critical acclaim that it has received. It's made a tremendous impact, and I want to begin with maybe this version of the podcast to make up for past sins on my part. Maybe it was a message to me. Do you believe in kind of the mysterious ways of serendipity, Michio, that maybe this was for a reason that we got to go together again for the second time?
Well, destiny, of course, is a very elusive quantity. But as I mentioned in my speeches, I think humanity has a destiny. Not individuals, but I think humanity has a destiny. The universe is a chess game. And our destiny is to figure out the rules of chess. And the rules of chess, of course, give you the God equation. And then we want to become grandmasters of chess. I think that's the destiny of the human race, to master the rules of chess, that is the God equation, and then to become grandmasters.
And when we talk about chess, we actually didn't have a chance to talk about this last time, but maybe this is a good time as any to go into this. I have a theory that we're already being beaten by computers and artificial intelligences when it comes to chess. Do you think an artificial intelligence could ever create a game like chess? In other words, does it have the creative power, even in a futuristic alpha infinity type computer? Could it create a game that humans would find amusing, or perhaps could it create a complex game, not just solve and beat us, but could it actually outdo us and create a game such as chess?
Well, first of all, let's take a look at artificial intelligence today versus artificial intelligence maybe in the next century and beyond. When we look at robots today, what animal are they equivalent to? If you were to compare a robot today to an animal, they would be equivalent probably to a cockroach. You could put a cockroach in a forest, and the cockroach would immediately find food, shelter, mates. You take our most advanced military robot and put it in the forest, and what happens? It falls over, gets lost, can't even get up again. But eventually they will be as smart as a mouse, then as smart as a rat, then as smart as a rabbit, then as smart as a dog or a cat. And by the end of the century, who knows when, I think they'll be as smart as a monkey. Now, monkeys are self-aware. Therefore, they are potentially dangerous as well. And at that point, we should put a chip in their brain to shut them off if they have murderous thoughts. Now, that's because monkeys are self-aware. Now, dogs, on the other hand, dogs are confused. You see, dogs think that we are a dog, and that's why they obey us. Because there's a pecking order in a wolf pack, and that's why they obey us. So we have a long ways to go, I think, before we have a device that is as creative and as spontaneous and innovative as human beings.
I think of you as a master storyteller, and people, you know that you have a wonderful reputation as a hardcore scientist, but I interviewed in the intervening weeks since we spoke, I interviewed Neil deGrasse Tyson. Mm-hmm. And he and I spoke about many things, including impact of race and issues of race, et cetera, but mainly about science and popularization, as well as the fact that he can no longer walk down the street and not get recognized. The day after you and I record our episode, you and I appeared together in William Shatner's Unexplained, the episode about the moon. And I was just remarking to one of my kids came in and said, "Wow, Dad, you're really important. Hey, look who you're appearing with." And I said, "Who? Captain Kirk?" William Shatner? He said, no, Michio Kaku. How do you take your fame and celebrity? How do you handle it and still do serious work when you know that some physicists look down on those of us who reach out to the public? How do you see the balance between your public persona on TV and movies with your private productive persona as a physicist?
Well, there's a sad story about Carl Sagan, the great astronomer. He, of course, was a publishing astronomer, made contributions to the field of astronomy, made discoveries. However, he was nominated for the National Academy of Sciences. That's the nation's highest scientific advisory body. It advises the United States Congress, for example. But the mathematicians at Yale revolted. And when the vote was taken, they basically said he is a, quote, mere popularizer, and they voted him down. And that was kind of an embarrassment to Carl Sagan. But now we have figures like Stephen Hawking, who have impeccable credentials as a research scientist. And so they're in a situation where they can say, yes, I want to reach the people. I'll be able to touch people's hearts and minds. Because, of course, ultimately, who pays our salary? It's the taxpayers, ultimately. And, during the Cold War, all we had to do was go to Congress and say one word that we would get funding. And that word was Russia. Then Congress would come back to us with two words. And those two words were, how much? Well, those days are gone. We had to learn to sing for our supper. And that was very dramatic in my field, elementary particle physics and relativity, in the 90s when the super collider was canceled. That's the reason why American particle physics is 2 generations behind Europeans, because there, of course, they have the Large Hadron Collider. What happened during those hearings? Well, in the last days of hearing, one congressman asked a physicist, and I quote, "Will we find God with your machine? If so, I will vote for it." Well, the poor man didn't know what to say. So he said, "We'll find the Higgs boson." Well, you can hear the jaws hit the floor of the United States Congress. Billions of dollars for another goddamn subatomic particle? The vote was taken and the machine was canceled. And since then, we physicists have racked our brains. How should we have answered that question? Because it'll come up again. Will we find God with your machine? I would have answered it differently. I would have said, God, by whatever signs or symbols you ascribe to the deity. This machine, the super collider, will take us as close as humanly possible to his greatest creation, Genesis. This is the Genesis machine. It will celebrate the greatest day in the history of the universe, its birth. Unfortunately, we said Higgs boson, and American particle physics, experimental physics, was set back 2 generations. Think about that. So we physicists have to learn to sing for our supper.
Hey friends, just a short request to ask you to use your thumb while my thumb is occupied to leave a like on this video. And don't forget to subscribe. It really helps us with the algorithm. Now back to the episode.
There's an awful lot of God that makes its way into things like the God particle, which I think it was pejorative originally for the God, hyphen DAM and particle by Letterman. But I wonder, if there isn't a meta layer on a higher level, this feeling that when you cancel something, the money goes back into the same field. In other words, there was a jealousy, just as there was of Carl Sagan, and I heard that story from people that knew Carl, obviously, but also there was almost like a jealousy of particle physics, that it enjoyed a whole century or half of a century at least of being the most preeminent regarded field of physics, wherein physics was the preeminent form of intellectual activity of all human beings, at least, where you had people like Feynman and others, Schwinger, escorted by armed guards to go to physics meetings. Like, I can't even imagine, going to the WWII or the APS meeting and having an armed guard next to me. I mean, that would be kind of fun, actually. But towards the end of the century, people started to think, well, what are we getting? What's the return on investment? And there have been, some books written about this. Peter Voigt has written about this. Lee Smolin has written about this. How do you answer the critics that say there haven't been major revolutions in fundamental particle physics since the 1974, November Revolution, I think it was called? How do you answer those critics that say that fundamental physics has been in a holding pattern for 50 years almost?
Well, there is a unspoken pecking order where, as you pointed out, some people are jealous that elementary particle theoretical physicists are at the top of the pyramid. And computer scientists call this physics envy. Physics envy, meaning that in physics, things get simpler every year, but more powerful. So when I write an equation down, I know that on the other side of the Milky Way galaxy, there's an alien with a different notation writing the same equation because these equations are universal. Now, you can't say that about Shakespeare. You can't say that about great works of art because, of course, they are particular to the planet Earth, specifically Homo sapiens on the planet Earth in a certain century, in a certain country, with a certain language. While physics, especially elementary particle physics, is universal. Plus, it gets simpler every year. While in English literary criticism, I have a lot of respect for them. Some of them are my friends who engage in English literary criticism. They wonder, what did James Joyce really mean by that? And PhD theses by the hundreds are written about what did Hemingway really mean by that sentence. So English literary criticism becomes more complicated every year. Theoretical physics is the opposite. You could put all the equations of the universe, the fundamental equations, on one sheet of paper. One sheet of paper. Now, can you do that with Shakespeare? Can you do that with Hemingway? No, but physics. The fundamental laws of physics can be put on one sheet of paper. Top of the line, Einstein's equations, 1 inch long. Then the standard model, which is ugly as sin, but you could put it on a sheet of paper. The theory of almost everything, a bunch of gibberish, 10 lines across. That's the standard model. And it didn't have to be that way. And so that's where physics envy comes into the picture. If you are a computer programmer, tirelessly working about computer games or algorithms for Wall Street, it gets complicated, but physics gets simpler and more universal and more powerful as the years go by. Now, are people jealous as a consequence? Yes, but that's human nature. Science progresses independent of the whims of jealousy and human nature. So physics will march forward no matter how jealous people are or how much backstabbing there is, because that's human behavior. You can't stop it. That's just the way it is. For example, when I got my PhD back in the 1970s from the University of California at Berkeley, if you were doing string theory, people laughed at you. They snickered. In fact, John Schwartz was in an elevator with Richard Feynman. And Richard Feynman was joking with John Schwartz and said, "John, how many dimensions are you in today?" In other words, Feynman liked to make fun of everybody, especially string theorists. And so the point I'm raising is we are humans. Therefore, we engage in petty kinds of behavior. But let me tell you my favorite Feynman story. I gave a talk on string field theory, which is my creation. It summarizes all of string theory in an equation about 1 inch long. And I gave a talk at Aspen for the Center of Theoretical Physics. Feynman and Gelman, two giants, were in the audience. Feynman being famous for putting down the speaker. Feynman comes up to me after my talk, and he says, "Well, I don't necessarily agree with string theory." But then he said, "Your talk was one of the most beautiful talks I have ever heard." In other words, summarizing this vast treasure trove of equations of string theory into an equation that is 1 inch long. He said, "Your paper was gorgeous."
Oh, well, that's high praise indeed. I'm going to come back with a retort from Feynman himself, which is that he said, "I don't care how beautiful your theory is. If it doesn't agree with the experiment, it's wrong." And you lost a bet a few years ago with a commentator, John Horgan, so-called bet over the string theory provability before 2020.
No, the Nobel Prize. With the Nobel Prize being given.
The Nobel Prize. Yeah, I forgot what did I say? Well, ignore what I said. But anyway, you made a bet under the auspices of the Long Bets Foundation, a public arena, that it would be there would be evidence for either superstring theory or membrane theory or some other unified theory describing all the forces of nature that would result in a Nobel Prize. So you lost that bet. You paid up, of course. Unlike some other people who didn't pay up certain bets, but we're not going to talk about those people. So I want to ask you, in light of Feynman's saying, how how long would you make that bet again? Would you make a 10-year long bet with me? How do you feel about the prospects for, I mean, I don't like the Nobel Prizes, these posters will tell you, as a kind of a sign of God's, kind of divinity bestowed upon mankind, because it's just given out by mortals, mainly in Sweden. And so who are they to judge us? But anyway, I want to ask a question. Are the prospects getting bigger, or would you dispute that quote with Feynman that the sine qua non is experimental testability?
No, I agree with Richard Feynman and also Carl Sagan. Carl Sagan said remarkable claims require remarkable proof. And 2 weeks ago, there was an earthquake that emerged outside Chicago at Fermi Laboratory, an earthquake that everyone is talking about in physics, experimental or theoretical. A deviation has been found in the standard model. Look, I got my PhD in 1972. The standard model was already in place when I got my PhD, and it held sway for 50 years. For 50 years, we have seen no crack in the standard model, even though it's the ugliest theory ever proposed in the history of science. 36 quarks and antiquarks, 3 generations of identical particles, 3 parameters that can be adjusted at will. It's ugly. It is clumsy. It's a theory that only a mother could love. And we found a crack in it just 2 weeks ago. People are jumping on it. We have 4 forces. We have gravity, the electromagnetic force, and the 2 nuclear forces. There could be a 5th force. A 5th force could emerge from the Fermi laboratories outside Chicago, and that's causing excitement. And what are the candidates for a 5th force? Well, it means a new particle. String theory has lots of particles. We here, in this universe of ours, we are the lowest octave of the string. In fact, if Einstein had never been born, we would have discovered general relativity as the lowest vibration of a string. However, the string has higher octaves, just like your piano, just like your violin has higher octaves. The higher octaves could be manifested, who knows for sure, in this new discovery. Plus, we have satellites going up, LISA, a gravity wave detector in outer space, that may detect evidence of a pre-Big Bang universe predicted by string theory. Not to mention the fact that the Chinese, the Japanese, and the Europeans are now proposing a successor to the Large Hadron Collider, which may very well probe the periphery of string theory. Not to mention the fact that there are ongoing experiments right now testing for deviations from Newton's laws of gravity as predicted by string theory. So in other words, there are plenty of experiments that are now being conducted. The people who don't know this are the critics.
Right. I was taking the opportunity between the previous time we conversed till today to look at some of your papers from the 1970s. And I found them remarkably prescient for those that have any doubt of Michio's calculational computational prowess. You've been at the New York at CUNY for a long time. I didn't realize how long that you were there since 1974 after getting your PhD. You work with Mandelstam, right, as your advisor? Yeah,
that's right.
So you are a proponent, and what I thought we'd do this time is talk a little bit with you playing the role of the defender of rivals to string theory. In other words, I'm going to pretend I am the proponent of string theory, and I'm kind of agnostic. I'm an experimentalist. I like to adhere to experimental tests, obviously, and even the cosmological tests. We'll get into that in a bit. But I'm going to say act as the defender, and I want you to kind of pick a theory that's a rival in your mind. It could be loop quantum gravity. It could be my friend Eric Weinstein's geometric unity. What do those theories have that can rival the Lagrangian, which you made not only the first relativistic field theory thereof, but you wrote down the Lagrangian that included matter fields. So these other models that you support in this argument in simulated space, you support loop quantum gravity and other things. They don't even include fermions. So what could you say about these rivals to string theory to defend them?
Well, first of all, what is the criterion to win a Nobel Prize and be declared the next Einstein? You have to satisfy 3 things. 3 things, and you will go down in history as the next Einstein. Your theory, your Lagrangian, must first of all have general relativity in it. Second, it must have the standard model and more, but at least the standard model. Third, it has to be mathematically consistent, that is, finite and anomaly free. That's it. And then the question is, how many theories can satisfy these criterion. Let's take them one at a time. There's something called loop quantum gravity, a very ingenious theory, I must admit. However, it has no electrons, no protons. You and me, we're not part of loop quantum gravity. It's a theory of pure gravity. And pure gravity is probably mathematically inconsistent. If you calculate the first Feynman loop diagram, I'm pretty sure it is divergent. We've done it on computers. We haven't done it in the regime for loop quantum gravity. But for perturbative gravity, we've done it on a computer. And it diverges. It blows up. It's infinite. Well, what about all the other attempts? Erwin Schrödinger tried to create a unified field theory. He's the founder of quantum mechanics, for God's sake. He failed. He thought that it was, again, a pure gravitational theory, no electrons, no protons. And so you go down the list, and then you begin to realize, oh my God, there's nothing left except one. And the only thing that is left is string theory. Now, if you don't like string theory, what is your main attack? Your main attack against string theory would be as follows. First, is it a theory of anything or a theory of nothing or a theory of everything? In other words, where's the beef? Where is the experimental proof? And I have a rebuttal to that. Second, it doesn't predict our universe. It predicts a multiverse of universes. And which one is ours? So a theory of everything becomes a theory of anything. And so it has no predictive power. You cannot predict anything a priori using string theory. So those are the two most powerful arguments against string theory, which I will be glad to address.
Yeah, and I will further attack loop quantum gravity by just saying that the foundation on which it's based, and maybe this is a technical point, but my understanding is that there are Hamiltonian formulations of it, but not Lagrangian formulations, or perhaps those don't exist. Can you specify or explain why is that an important distinction? When you say the Lagrangian of string theory that you worked on from the 1970s until today is the kind of the necessary ingredient of a starting point for a universal theory of everything. Can you say why the loop quantum gravity should even be considered, given that it doesn't have a fully fleshed out standard model of particle forces and fields?
Why is it that relativity and the quantum theory don't like each other? Why should God have a left hand and a right hand that fight each other, that don't coordinate? I mean, that's ridiculous. Why would God create two hands that don't coordinate with each other? Well, the problem is that gravity is based on smooth surfaces, smooth, elegant, beautiful, gorgeous manifolds, while matter is based on chopped up particles that you grind up and spit out like a meat grinder. It's all cut up. And so loop quantum gravity, in which field does it fall into? It falls into the gravity field, but says nothing about electrons, protons, quarks, mesons, the hundreds of particles that we have analyzed is a theory of pure gravity. And therefore, it is simply not a unified field theory, which even the creators of the theory acknowledge. They'd be the first ones to say that their theory is not a rival to string theory. It's just an alternative for gravity, but not for electrons, protons, quarks, you and me, basically. Mm-hmm. And so we have a situation where, of all the theories proposed, these two theories, relativity and quantum theory, don't like each other. One is based on smooth manifolds, like trampoline nets, and the other one is based on chopped up particles. And how do you combine these two? The only way to combine these two is through music. And that is the lowest octave of the string contains all of Einstein's theory. If Einstein had never been born, we would have discovered the entirety of general relativity as the lowest note of a vibrating string, which is, I think, amazing. In fact, the standard model is also there among the lowest octave. The problem is everything else is there too. Universes that don't exist. Universes where protons are unstable and matter cannot form. Universes that are different dimensional. They're all there in string theory. How does it select out our universe out of this wide range of universes?
Right. Yeah. So for me, one question I've come up with, I've spoken to many proponents of string theory from Cumberland Baffa, John Preskill, others. And, the question I keep getting, not so satisfied by their answers, I'm going to pose to you, which is that it's not at all clear that that having somebody like my former guest, Leonard Susskind, on saying that there's a landscape of possible vacuous states. And this is told to me as an experimentalist to imply an almost unbounded number of possible string theories, string values of fundamental constants, values of masses of the fermionic sector, the bosonic sector. You can describe in any way you like. It can construct a landscape of possible of universes that we find ourselves just in one. And there's always the anthropic kind of result that then implies. But it's not all clear to me, Michio, and maybe you can clarify for me. But why would these other universes not also have laws where 1 + 1 doesn't equal 2? Because what they call addition is what we call quaternionic multiplication. In other words, that the laws of math, the laws of logic, why couldn't they differ from universe to universe in the string landscape?
Well, let me try to answer this question by posing another question. How many solutions of Newton's laws are there? And Newton lived in the 1600s. How many solutions are there? There's a solution for a gun, for a rocket ship, for a pellet, a marble, a spinning top. In fact, there are an infinite number. There's a landscape. There's a landscape of infinite sequence of solutions to Newton's laws of gravity. Maxwell's equations for light. How many solutions of Maxwell's equations are? Infinite number. So how do you determine which one is your universe? You have to tell me. You have to tell me that we're describing a rocket today, or we're describing the Empire State Building today. You have to tell me this. You have to tell me, quote, the initial conditions. Okay? Same thing. If I have a theory of everything, not string theory, but an alternative. If I have an alternative theory of everything, it has the same problem. It will give you an infinite number of solutions depending on your initial conditions. So where do the initial conditions come from? You tell me. Now, at the instant of creation, we're talking about 10 to the minus 33 centimeters with the Planck length of energy. That's the energy of the Big Bang itself. The universe started off as a quantum fluctuation in the vacuum. Now, given that fact, what are the initial conditions at the instant of creation? We don't know. That's an experimental problem. That's for you guys. That's where the weak link is experimental physics. When the experimental physicists tell us that we're talking about a spinning top, a bullet, a rocket ship, then we can solve the equation. But until the experimentalists tell us what the initial conditions of the universe were, we're stuck, because that's an experimental problem. In other words, it's your fault.
I'll take the blame for that. That's the least thing I've been accused of today alone, Michio. But let me refer you to the work done by David Spergel, Daniel Holtz, Maya Fishback, and Chris Pardo back in 2018, which is titled Limits on the Number of Space-Time Dimensions from Gravitational Wave 170817, which very severely limited and constrained the dimensionality to be very close to 3 dimensions of space, in contradistinction with an uncertainty of at the few percent level from a single event, by the way. I mean, this will only get better. So does this not rule out vast tracts of land, many acres in the string landscape? I mean, almost infinitesimally shrinking it to a single, if you like, boundary condition, because as you know, Newton's laws are very different in the universe of 3 spatial dimensions versus 2 or 1 or 4 or 5. So do these limits shake your confidence at all in large extra dimensions or in string theory as a whole?
No, these are all speculations. I think these speculations are healthy, but until we have the God equation, that is the final formulation of string theory, all these are nothing but speculation. Now let me explain. My equation, string field theory, allows you to summarize string theory into an equation a little bit more than an inch long. In fact, I published it in my book, the God equation. However, that's not enough. We now have the 11th dimension coming in from Princeton's physicist department, and we know that there are membranes. Now, do we have a string field theory for membranes and strings? The answer is no. Now, maybe somebody who's listening to this program will be inspired to write down the field theory of membranes and strings. And I have a word of advice for them. When you find this final equation, the God equation, tell me first. We'll publish together and we'll win the Nobel Prize together, and we'll be declared as the joint creators, the successors to Albert Einstein. Because that's what we're talking about. We're talking about the Lagrangian, which is probably an inch long, which will summarize both membranes and strings. That could be the whole shooting match.
You obviously think geometrically. I remember reading your books in the 90s and being heavily influenced on them. Not quite tempted to become a theoretician myself, but nevertheless very influenced by you and the exquisite way that you spoke about kind of the two sides of Einstein's equations, one kind of marble and one made of wood, and thinking about the hyperspace, kind of conjectures. Are those possible to rule out with any experiment? As Nathan Seiberg said, we string theorists are very arrogant. If something comes along and is successful, we will call it part of string theory. In other words, if by saying that we need to, get more and more data, essentially, is there a falsifiable element to string theory? Is there any experiment or combination of experiments that would cause you, Michio, to reconsider your claim that the God equation will ultimately be found? In other words, is there hope? Is it hopeless to convince you otherwise, or because of your deep-seated convictions and work in the field, or is there really a chance that string theory could be wrong?
Every theory has to be testable, reproducible, and falsifiable. That is what we call science. And there are ways to test string theory. Let me just rattle them off real quick. 5 possible ways to test string theory. One is to look for deviations in the standard model, like what happened 2 weeks ago. The first major crack in the standard model was found. Maybe it's the photino, or maybe it's a higher supersymmetric partner of some of the particles that we see today, predicted by string theory. Second, LISA, Laser Interferometry Space Antenna, sponsored by the European Space Agency and NASA. We want to get a gravity wave detector in outer space, giving us baby pictures of the instant of creation when it emerges from the womb. And if we get baby pictures of the infant universe emerging from the womb, maybe we'll find an umbilical cord. An umbilical cord, because string theory does not stop at the instant of creation. String theory goes before the instant of creation. There's a multiverse of universes out there. And so we can talk about pre-Big Bang physics. How do we do that? We look for post-Big Bang radiation and then run the videotape backwards using string theory equations to get radiation profile from before the creation of the universe itself. That's number 2. Number 3 is dark matter. There are experiments going on right now, even as we speak, looking for dark matter collisions with protons. The spark created by such a collision will be photographed, and that could signal dark matter on the Earth. You see, we live in a wind of dark matter. Right now, there's dark matter penetrating your body, but it's not electromagnetically charged, so it's very difficult to detect. It's like a neutron, very difficult to detect. But any day now, I'm not sure when it'll happen, but we're going to detect evidence of dark matter in the laboratory and also dark matter in outer space. Fourth, we're talking about the fact that the Chinese, the Japanese, and the Europeans are now looking at post-LHC physics. They're looking at the next generation of particle accelerators, which may find, who knows, supersymmetry, the symmetry of the string. And fifth, we're looking for deviations from Newton's laws of gravity. The inverse square law we learned about in high school. Gravity diminishes as the square of the distance. If you're twice the distance, gravity goes down by a factor of 4. But no one's ever tested that in your living room. So in outer space, we know that the inverse square law works for galaxies, works for stars, planets, but we don't know whether it works for your living room or not. So we're going to test it. We're going to test the inverse square law to see whether or not there's an inverse cubic or inverse quartic or quintic corrections to Newton's laws of gravity. So there you have it. 5 experiments that could be done to prove that the string theory is a theory of everything, or a theory of anything, or a theory of nothing.
Let me ask you another philosophical question, which is that, and I had this conversation with Sir Roger Penrose after he won his Nobel Prize, I said, Sir Roger, you and Stephen and others worked on the singularity theorems, black holes, and origin singularities. Of course, Stephen went astray in some sense and really made this case in the brief history of time that the universe emerged in the so-called Hartle-Hawking state, and that time had no boundary and effectively can be instantiated in what he called a trick in the book. And a few people really have read it all the way through, because he says it's a trick just to think about things mathematically. And then he goes on to say, because of this, the universe doesn't need a beginning, and therefore one of the two roles for God has been eliminated. In other words, God had two purposes, according to Stephen. One was to initiate the universe, and the other one was to instantiate the laws of physics. He said that law of property number one of God was invalidated by the no boundary theorem. Property number two would be invalidated in his later book, The Grand Design, via M theory. What do you make of these two claims? First of all, does any practicing theoretical physicist believe that the no boundary condition is accurate? In other words, that physical instantiation of time itself contains no boundary because of this Wick rotation that he did to the complex plane for time and described in A Brief History of Time. Do any of your colleagues in theoretical physics actually take that seriously currently?
Well, first of all, I am no judge of Hawking's no boundary theorem. I don't work in that field. However, to answer your question, am I aware of people who work on it actively? And the answer is no. Mm-hmm. I don't think personally, this is my personal opinion, not objective. My personal opinion is most people think of it as a curiosity, a mathematical trick. You simply add the square root of -1 to the equations and boop, your singularity disappears, okay? It's a sleight of hand. Physics is subtle. It's not just a sleight of hand that you can do by putting an extra I in your equations. You don't make your equations work just because you put an extra square root of -1 in the equations. But again, I'm no authority in this field, but to my knowledge, no one really takes it seriously. Mm-hmm. Also, Hawking had another argument against the existence of God. He had several. The other one was that the Big Bang happened so quickly that there was no time for God to create the universe. The universe was simply there. And, to create a universe, it takes a lot of work. Creating a universe is not easy. And there was no time to create the universe. But you see, if string theory is correct, then there was a pre-Big Bang universe, a universe before the collision of our universes to create our known universe. So a bubble bath, universes in a bubble bath, bubbles can collide, bubbles can fission. So there's a time before the collision of two universes. So there's a time before the Big Bang in string theory.
Just pivoting a little bit, I have an unusual background in that my parents were both born Jewish, biologically Jewish. I was then baptized in the Catholic Church, and then I became an altar boy in the Catholic Church. Then I became an atheist. Then I became a practicing Jew / devout agnostic. You have a similar background. Your parents were Buddhist. You were raised Presbyterian. Now you call yourself agnostic. Explain what agnosticism means in practice. Do you do anything that theists believe in, that they practice? Do you go to church, or do you stay home like Richard Dawkins?
Some people have tried to disprove the existence of God, but that's like trying to disprove the existence of unicorns. You can't do it. It's logically impossible to disprove a negative.
Just come to my daughter's room. My daughter's bedroom is full of unicorns.
Yeah, I mean, even if you say that we've looked for unicorns and we can't find unicorns anywhere, somewhere, some place that you've never looked, never even thought of looking, could harbor a unicorn. So it's very dangerous to say that some things don't exist. So when some people say that God doesn't exist, you can prove it. Well, maybe God exists in a place that you didn't look for. Now, I believe in the God of Einstein. So let me explain. Einstein did not believe in a personal God. He did not believe that, your Christmas presents are given to you because God wanted you to have that bicycle for Christmas. God doesn't smite the Philistines, walk on water, or all those things. But he did believe in the God of Spinoza, the God of beauty, harmony, elegance, simplicity. The world could have been random. The world could have been chaotic. The world could have been messy. The universe could have been awful. But here we are as conscious beings contemplating the fact that the laws of physics can be summarized on one sheet of paper. Now, it didn't have to be that way. Our universe is gorgeous. Think of what our universe could have been versus what our universe really is. We have conscious life in a universe that started off in a random state. And so that's why I think that, as Einstein figured, humanity is like a little boy or a girl going into a library for the first time, and there's this huge storehouse of knowledge, and all we can do is get the first book, look at the first page, read the first paragraph. That's all we can do. But in front of us, there's this ocean of knowledge, and it didn't have to be that way. It could have been messy, chaotic, ugly, random, but here we are in a universe where the laws of physics, the ultimate laws, you can write on a sheet of paper. In fact, I think you can get it down to 1 inch.
Well, with my handwriting, it would be hopeless to fit it in anything other than a poster-sized format because I have terrible handwriting. But Michio, I want to ask a question. Is it not presumptuous, since we don't have even a grand unified theory that everybody agrees to? In other words, we have candidates, SU5, we have Petit Salam, we have other candidate theories, as I mentioned. Is it presumptuous? Is it not like going from, say, Einstein unifying the law of gravity on Earth to the laws of gravity of the moon, from apples to satellites? Would it not be like going from that to, the electroweak unification? In other words, are we putting, the cart before the horse a little bit too much, looking for the God equation before we find the Jesus equation? I don't know, the equation just right below the God equation.
Well, some people talk about a desert. That is, if you take a look at the energy of our particle accelerators, they're low energy. We can go to 14 trillion electron volts. And up to that point, there's hundreds of particles that we can discover. Some people think that beyond that, we're going to see a desert. Almost no subatomic particles at all. Now, why is that? Because the next energy realm is atomic energy. That's 10 to the 19 billion electron volts. That is a quadrillion times more powerful than the Large Hadron Collider. Some pessimists say that from now, with the Higgs boson, till the Planck energy, there's a desert. Now, we can't rule it out because we don't know when supersymmetry kicks in. Now, let me explain. Symmetry is the language of the universe. Symmetry allows you to combine two things that look dissimilar. E equals mc squared, for example, unifies E with M, unifies matter with E, and M is the hydrogen of the sun, and E is the sunlight that we get from the sun. So we look for symmetry. Now, symmetry, we don't know when supersymmetry kicks in. Many people believe it, and even the critics of string theory thinks that supersymmetry may kick in as the symmetry of the string, but when? At what energy will it kick in? So there is a criticism that says that there could be a desert there. No matter how big a particle accelerator we build, we will find nothing, just the standard model. Now, I don't believe in that, but you can't dismiss it easily because there are some people who propose that idea, the idea of a desert.
I've talked with Sheldon Glashow on the podcast a couple of months back, and he's obviously been quite a critic in some ways of the of string theory as it is, and even spoken in terms of it almost presenting a danger. I don't want to get back into that kind of debate, but I do want to think kind of more broadly when we think about these big items like the existence of a possible string landscape or the existence of a multiverse. What is it about that necessarily connects to God? For example, if I go to my neighbor who has a lab down the hall, she studies condensed matter, field theory, condensed matter phenomenology. So, she might be looking at Chern-Simons topological defect matter. And so how come they don't talk about God as much as we seem to do in the cosmology and fundamental physics theories realm do?
Well, it starts with Einstein in the sense that he said that science without religion is lame, but religion without science is blind. And so if you read his works, they're littered with references to God. Again, not the personal God, the God that you pray to, the God that you want to get that bicycle for Christmas. No, we're not talking about that kind of God. And the public is also fascinated by God. Just a few years ago on auction, the Einstein God letter went up for auction, and people estimated that it would pull in maybe a few million, a few 100,000. People were shocked. People were shocked that that collectors were willing to pay $1 million to get Einstein's God letter, where he lays out his position on God, that he doesn't believe in a personal God, but he does believe in the God of Spinoza. So it's out there. Now, also in mathematics, there is a God equation in mathematics. If you're a mathematician, you know that certain numbers are sacred. 1, 0, I, and pi, and e. These are the sacred numbers of mathematics. There's one equation, the Euler equation, which summarizes all these fundamental causes in one equation. That is sometimes called the God equation. Of course, it's pure mathematics. So of what practical importance is it? Nothing, or very little anyway, because it's pure math. However, think about it for a moment. God equation of physics on the same scale as a God equation of mathematics would unify the fundamental features of not just math, but the universe, because that's what physics is all about, the equations of the universe. And so the fact that there could be a God equation for physics, to me, is astounding, absolutely astounding, because there's already a God equation for mathematics, but a God equation for physics would be a theory of all physical phenomena, which in turn gives rise to chemistry, gives rise to biology, gives rise to you and me, give rise to love, everything that we enjoy about the universe emerging from one equation.
So I want to conclude this second edition of our podcast with kind of just a brief history of your time on Earth. You have an amazing story. You were born to parents that I understand that they were interred in World War II as citizens. It's an awful epoch in the American history. Did they ever harbor resentment towards the government? How did they react on a personal level, if you don't mind describing it? It's such a unique horror in our history. How did that impact you? Did it impact them? If you care to talk about that, I would appreciate it.
First of all, my parents were U.S. citizens, but nonetheless, in 1942, they were locked up and kept behind barbed wire, kept behind guns, kept inside a camp. Their funds were pretty much confiscated. You had 2 weeks, if you were lucky, you had 2 weeks to liquidate all your assets. And so it was heartbreaking knowing that your neighbors that you've known for a generation would come up to your house and bid pennies on the dollar for all your household heirlooms, because you could only take what you could carry on your back. So they had to liquidate. And again, some people had to liquidate farms. They had to liquidate greenhouses. Mm-hmm. The Japanese were the ones who drained a lot of the swampland of California and created this breadbasket called California. And a lot of it was done by Japanese. And after the war, they came back and it was all gone. They found their neighbors living in their homes. And of course, it was after World War II, so they really couldn't say much about it. The Supreme Court, even though individual justices have spoken against it, to their credit, the court itself has never made a landmark decision showing that it is unconstitutional. Mm-hmm. So some people who are experts in the Constitution say there's a loophole there, that in case of a crisis, the McCarran Act and other acts could be reinstated, in which case people could just be locked up and put into the camps by the hundreds of thousands. 110,000 Japanese Americans were incarcerated during that time. Now, my parents, their philosophy was very practical. You pick up the pieces and you move forward. You do not have a chip on your shoulder. Of course, you want to make sure it doesn't happen again. You want to make sure it doesn't happen again. But you don't want to have a chip on your shoulder either. And you want to do your best. And unconsciously, I sort of knew in the back of my mind that if I was going to be anything in the world, I would have to be, quote, extra. I have to put more on the table than the average person. No one told me that, but I just sort of figured it out, that if you want to be considered equal, maybe you should be a little bit better than equal. Mm-hmm. But like I said, I'm not going to come out with a chip on my shoulder. I think that we learned the lesson. We have to make sure that the Supreme Court unconditionally rules that as unconstitutional, while it has not yet done so. And I think we'll be in a better place as a consequence.
Yeah, I agree. I mean, looking at, the current climate where people are going back to the founding fathers of the country and rightfully, understanding or wanting to, put in context the fact that many of them owned slaves. I mean, this is in the living memory what happened to, as you say, U.S. citizens, and not at all to diminish the horrors and the moral inexcusability of human slavery. But this is still within our generation, and yet President Roosevelt is held up with such high esteem and so forth by many members of society. I don't feel like we've reckoned with that, with what we did to our fellow citizens back then. But I do want to, compliment you and your spirit, which, immediately went to you being, constructing a particle accelerator not far from UC Berkeley, where the particle accelerator was born as a young person. And maybe we can close out with that, because one thing I usually ask my guests is, do you think that creativity, Michio, can it be taught? Were you born with these kind of creative abilities? Did you have to work extremely hard at this? This is something Neil deGrasse Tyson took me to task for, essentially criticizing, the assumption that, he was just born with a gift. Were you born with a gift? Were you born with the ability to do hard work, which I consider a gift? What do you attribute your success in terms of your creativity and throughput as a scientist?
Well, my philosophy is, first of all, we are all born scientists. We're born wondering where we came from, why the stars shine, why the sun shines. We can't help it. We're just born scientists until we hit the greatest destroyer of scientists known to science. The greatest destroyer of scientists known to science is junior high school. When you go to junior high school, science is made boring. Science is made memorization. Is being having to know things that are totally irrelevant to people's lives. You know in the back of your mind that you're never going to use that piece of knowledge ever again, and you're more or less right. Science is not relevant to people, and science becomes giving names to things. Richard Feynman, the Nobel laureate, told this story that when he was a child, his father would take him into the forest and show him how birds evolve, coloration, beak, how they feed, and so on and so forth. And one day a bully comes up to Feynman and basically says, "Hey, Dick, what's the name of that bird over there?" And the young Feynman did not know the name of the bird. So I'll paraphrase. The bully then says, "What's the matter, Dick? You stupid or something?" And in that instant, Feynman realized the difference between science and the appearance of science. That science is about principles, concepts, physical models and pictures. That's what science is about, not giving the names to birds. Of course, you have to know some names, but that is not science, giving the names to things. And so I think that's something that we have to realize, that young children were born scientists till it's crushed out of them when they hit junior high school.
Reminds me of a joke that I sometimes tell, where I took a class in ornithology as an undergraduate at Case Western Reserve University. And we studied hard their migration habits, their mating habits, their dietary habits, all these things about birds, their evolution. And then the final exam came, and all that was on the test were bird prints. And we were supposed to identify this bird from its bird track that looks like this, and this one. And birds have almost all the same footprints, at least in phenotype, so to speak. And I got so frustrated, Michio, that I handed in my paper and I didn't put my name on it in this huge class of 150 students. And as I'm storming out, fuming mad, the professor says, wait, you didn't write your name on it. And I said, "Professor, figure it out." I held up my foot. He didn't laugh, and you're not laughing either, but that's okay. Not all my jokes are so spectacular. But Michio, what is spectacular is your book, The God Equation, a bestseller in the New York Times, a bestseller on Amazon. Hundreds of thousands of people are going to be exposed to a concept that is mind-blowing, but presented by one of the foremost experts, the person who came up, if you're out there, my audience is expert. He basically, Michio, I think I can brag for you. You came up with the Feynman diagram type exposition for strings back in the early 70s. I mean, when string theory was a newborn, we talked about its umbilical cord. Well, the umbilical cord goes straight through Michio Kaku, the father of string field theory, the governing Lagrangian, the space-time tube diagrams, the Feynman diagrams. There are 11 of them in your original beautiful paper, which is a work of art, by the way, in a time when it was very difficult to make art and illustrations in papers. But Mitch, I want to thank you so much for your graciousness, your generosity with your time. This is our second interview. I'm going to try to salvage some of the previous one. But I want to especially commend you on this wonderful new book, The God Equation, and I'll let you know when this interview comes out. But for now, I want you to know how much of a positive, wonderful impact you've had on my multiverse.